Hello everyone, welcome back to my channel. If you are preparing for a coding interview, a university exam, or you just want to build better software, there is one algorithm you absolutely must know inside and out. It's fast, it's elegant, it's used everywhere in the real world. I'm talking about quicksort. Now, I know algorithms can sometimes look confusing when you read about them in textbooks. All those textbook definitions can make your head spin. But today, we are going to throw away the confusion language. We are going to break down quicksort using simple visuals, step by step, tracing example, and real code in both Python and Java. By the end of this video, you won't just memorize quicksort, you will actually understand exactly how it works. So let's move on. Before we dive into quicksort itself, let's take a quick step back and ask a fundamental question: what actually is sorting? In data structures and algorithms, sorting is simply the process of arranging random data into a specific meaningful order. Think about shopping online. You always filter products by price, right? That's sorting in action. Generally, we sort data in two ways: ascending order, descending order. In ascending order, this means moving from smallest to value largest, like climbing upstairs from 1 to 5, as you can see. In descending order, this is the exact opposite. We go from largest value down to the smallest, like walking down those same steps 5 to 1. While the concept is simple, how a computer actually moves those numbers around can vary massively depending on the algorithm you choose. If you have been studying data structures and algorithms for a bit, you probably know that quicksort isn't the only player in the game. We have a whole toolbox of options. For example, bubble sort works by repeatedly comparing and swapping near numbers. Selection sort continuously hunts for the smallest element and bring it to the front. Insertion sort builds a sorted list one item at a time, like sorting a hand of playing cards. And then we have the heavy hitters, merge sort. It chops the array in half over and over again and then merges them back together. But today's try is quicksort. Instead of comparing everything sequentially or breaking things blindly in half, quicksort uses a totally unique strategy called pivots and partition. Let's see what makes this strategy so special. So what is the core secret behind quicksort? First, it is incredibly fast, and it achieves this speed by using classic programming paradigm known as divide and conquer. Instead of looking at messy pile of numbers all at once, quicksort selects one single element from the array to act as baseline referee. This referee is called the pivot element. Depending on the order you want, the rule changes slightly. For ascending order, smaller values move to the left, larger values move to the right. For descending order, larger values move to the left and smaller values move to the right. That's it. That is the golden rule of quicksort. Let's look at how this split our workload. To visualize this clearly, think of the divide and conquer strategy as three-step process. Divide. We take our big unsorted array and split it into smaller sections based on that pivot referee we just talked about. Conquer. We take those smaller sections and sort them recursively. This just means we treat each side as brand new mini array and apply the exact same pivot rule to them. Combine. Here is the best part of about quick sort. Unlike merge sort, there is no heavy lifting required at the end because our partitioning process naturally forces items into their correct sides relative to the pivot. Once the subsections are sorted, the whole array is automatically combined and perfectly sorted. Let's see how this works in real life with an actual example. Imagine we are given this completely scrambled array of numbers from 1 to 9. 8, 3, 5, 1, 9, 2, 7, 4, and 6. To start sorting this as in ascending order, we need to pick a pivot. Now you can technically pick any element as you pivot, the first one, the last one, or random one. For this walkthrough, let's select the number 7 to be our pivot referee. Our mission now is to scan through the remaining numbers and filter them based on our pivot value 7. What happens when the partitioning loop runs? The algorithm looks at every number. Numbers like 3, 5, 1, 2, 4, and 6 are all smaller than 7, so they get pushed over to the left side. On the other hand, 8 and 9 are larger than 7, so they form a group on the right side. Now look closely at the screen. Even though the left side and the right side aren't fully sorted yet, the number 7 is now sitting in its exact perfect final position. It will never have to move again. For the rest of the algorithm, this is the magic of the partition process. Now that 7 is locked in a place and the conquer phase kicks into high gear, the algorithm temporarily ignores the right side and focuses entirely on the left subarray. That's me 3, 5, 1, 2, 4, 6. Because this is the recursive algorithm, it runs the exact same code on this subarray. It picks a new pivot within this group, let's say it's pick 4, and partitioning everything around it. As we push deeper into the recursive tree, the elements continues to break down into smaller and smaller clusters, separating into groups like 3, 1, 2, and 5, 6. We keep repeating this splitting process until we hit our base case, an array with a single element or an empty array. A single number is sorted by default. Once those base cases are reached, the recursive step unwinds, passing the sorted pieces back up the line. Boom! Look at that. As the recursive calls finish up, our left side naturally recognizes itself into 1, 2, 3, 4, 5, 6. Our right side referably finish as 8, 9. When we place them back around our original pivot element 7, everything snapped together perfectly. We have successfully transformed a completely scrambled mess into beautiful sorted array from 1 to 9. Now let's see how easy this is to write in code. If you're a Python developer, you can write quicksort incredibly cleanly using list comprehensives. Take a look at the function on screen. First, we check our base case. If the length of the array is 1 or less, we just return it immediately because it's already sorted. Otherwise, we pick our pivot. Here we are grabbing middle element. Then we use 3 simple lines partition our data. we get all items smaller than the pivot into a list called left. All item equals to the pivot into middle. And all items larger into the right. Finally, we just return quick sort left plus middle plus quick sort right. It reads almost exactly like plain English. For my Java developers out there, we can see the native recursive method structure right here on the slide. Inside our quicksort method, we pass our array along with its tracking boundaries, the low and high indices. First, we establish a guard check as long as low is less than high. We call our helper function called partition. This partition helper does the heavy lifting under the hood. It processes the element swaps directly within the original array memory boundaries, locks the pivot element into its final spot, and returns that index location as pi. From there, we recursively call quicksort on everything before the partition from low to pi minus 1 and on everything after the partition from pi plus 1 to high. Let's talk numbers. Why do engineers love quicksort so much? As you can see from our complexity table on the slide, in the best and average case scenarios, quicksort runs at an incredibly fast time complexity of O n log n. This happens when our pivot choices successfully split the data into relatively balanced halves. However, you do need to watch out the worst case scenario, which is O n square. This happens if your array is already completely sorted or reverse sorted and you repeatedly pick a poor pivot like the first or last element. This causes recursion tree to become completely lopsided. For space complexity, it takes a clean O log n memory space to manage the recursive call stack frames, making it highly memory efficient. Because it's highly efficient, quicksort is an absolute industry favorite. It is used under the hood of enterprises' database systems to index and query millions of records. It helps search engines sort and rank websites in milliseconds. It's used by your operating system File Explorer to organize files by date or size, and it powers the sorting filters on your favorite e-commerce platform so you can shop effortlessly. Let's do a quick recap of what we learned today. Quicksort is the powerhouse built on a divide and conquer philosophy. It uses a pivot element to cleanly split data spaces into smaller groups. It modifies data efficiently, making it a go-to choice for massive real-world application. Thank you for watching. I hope you enjoyed this presentation and found it helpful. Keep coding, keep practicing, and I will see you all in the next video. Bye.